Types of aqueous solutions. Salt water and sugar water. You encounter these in the kitchen at home. Cup of water, teaspoon of sugar in one cup, another cup of water, teaspoon of salt. You stir them up. It looks like exactly the same thing is happening, right? Sugar and salt actually look very similar, but they taste really different, don't they? Salt water is a homogeneous solution, a mixture of sodium chloride and water. Sugar water is sucrose and water. How do those things dissolve? How does that even happen? Have you ever just taken a step back and thought about that? How crazy is that? Why does salt dissolve in water, but if you put a teaspoon of sand in water, it's not going to dissolve? Pepper won't either. It'll float around, make the water look dirty, but it won't dissolve, right? Some things dissolve, some things don't. So let's talk about how something dissolves. There are competing forces, competing attractive forces when you put something like salt or sugar into water. You have forces of attraction between the solute molecules. That's what holds them together and makes them a solid in the first place. If there were no forces of attraction between these particles, it would be in the gas state and they just float around and take up the whole room. There are solvent-solvent interactions also. In water, the reason that water is a liquid is because there are attractions between the molecules. When you put these two together, now you also have attractive forces between the solvent molecules and the solute particles. And whether something will dissolve or not depends on the relative strengths of these different interactions. If you have strong attractions between the solvent and the solute, it will overcome the attraction between the solute molecules and it will dissolve. So this is a space-filling model of a water molecule. The big red here is the oxygen, and these are the hydrogens. What we're looking at here is the electron density. We talked a little bit about covalent bonds and how the hydrogen and the oxygen are bonded together because they're sharing some electrons. You can share something without it being fair or equal, right? You can break a cookie in half, but one half is bigger than the other, right? And so you give the little half to your little brother and you keep the big one for yourself, right? I shared. Little brother's crying because he got the little tiny piece. Oxygen and hydrogen don't share their electrons evenly. Oxygen's a bully and hogs the electrons. Okay, so what happens is we have more electron density over here and less by the hydrogens. And so we have an unequal distribution of charge. So this end of the water molecule is slightly negative and the hydrogen ends are slightly positive. It's not an ionic compound. This is not a +1 charge. It's a fraction of a +1 charge, maybe 0.15 or something, a little bit of charge. But even little things can be really important. So when we put sodium chloride into water, sodium chloride has sodium ions and chloride ions. They are very strongly attracted to each other because of their opposite charges. In order for the sodium chloride to dissolve, that attraction has to be replaced with some other attraction. So to pull these guys apart from each other, well, the sodium looks over here and sees the negative end of a water molecule and is attracted to that. What's actually going to happen is a whole bunch of water molecules are going to come and be attracted to the sodium. And they're going to lure the sodium ion away from the chloride. The chloride would come with it, except she's a bit distracted by the positive end of the water molecules near her. And so there's a force of attraction between the positive end of water and this negative ion. Water is not an ionic substance, but it does have positive ends and negative ends. So what happens is the sodium ion here gets surrounded by water molecules, and they're going to point their negative ends toward the sodium ion, and other water molecules are going to point their positive ends towards the negative ions. You could think of water as being like a two-faced friend, right? You know, they're really nice to you sometimes and really mean to you other times, or they change their behavior based on who they're with. So here we're going to put on our negative side to be attractive to the sodium ion, and here we're going to put on our positive side to be attractive to the negative ion. And the result is that you have ions that are free to move about in the water. They're actually sort of accompanied by this little entourage of water molecules. It's like, you know, a famous person walking around. They've got all these fans clustered around them. Everywhere they go, they've got people following them. But those ions are free to move. Electrical current is the flow of electrons. It's electrons moving. In order for electrons to move, there has to be something that allows them to move. These ions can move electrons through the water. And so it allows the solution to conduct electricity, whereas the pure water does not conduct electricity. So we talk about electrolyte solutions and non-electrolyte solutions. And electrolyte, this word, you've probably heard it in reference to what beverage? Gatorade, right? Oh, you need to replenish your electrolytes. Electrolytes are soluble ionic compounds. When you sweat a lot because you are exercising, you lose a lot of salt, and you have to replenish that in some way. So electrolytes are substances that will dissolve in water and form solutions that conduct electricity. There's actually a lot of electrical stuff going on in your body, and that's why you need salt. Not just sodium chloride, but other salts as well. So basically, electrolytes are soluble ionic compounds. And then we have non-electrolytes. They do not form ions when they dissolve, and they do not conduct electricity. So most molecular compounds, most molecular compounds, there we go, are non-electrolytes. So salt solutions conduct electricity, sugar solutions do not. Here's an illustration of a conductivity experiment where we have a battery attached to a light bulb. And if you touch these two wires together, the light bulb will go on. But they're not touched together. They're separated and they're stuck into this beaker of liquid. If we put table salt into the water and stir it up, the salt dissolves, forms ions, and that can carry the current. The light bulb lights up. If we do the same thing with sugar, the sugar also dissolves in the water, but it doesn't form any ions, and so the light bulb does not go on. It's a non-electrolyte. So here's an illustration of what sugar does when it dissolves in water. If we look at this space-filling model of sucrose, we see it has oxygens and hydrogens as well. And just like in water where they don't share the electrons equally, they don't share them equally here either. Oxygen hogs them. And so each of these hydrogens will be slightly positive, and that will be attracted to the negative end of the water molecule. And the slightly negative oxygen atoms in this sucrose molecule will be attracted to the positive ends of the water molecule. And so the sucrose molecules will separate from each other and they will float around in the solution, but because there are no ions, the solution does not conduct electricity. It's a non-electrolyte. Acids are molecular compounds, but they ionize when you put them into water and they form hydrogen ions. So something like acetic acid, when you put it into water, it's going to form acetate ions and hydrogen ions. It's not an ionic compound, but it forms ions. Strong acids are acids that ionize completely. When you put hydrochloric acid into water, there are no intact molecules left. They all come apart into hydrogen ions and chloride ions. With a weak acid, only a small percentage of the molecules ionize. Most of them remain as intact molecules. So HF is a weak acid, acetic acid is a weak acid. Here we're using a double-headed arrow instead of a single-headed arrow pointing only to the products. because this reaction, we'll learn a little later about equilibrium. This is actually an equilibrium. It's going both ways. And you can't tell just from the reaction equation how much of each is present. This arrow implies that it goes completely. Yes?
How do you know what's a strong acid and what's a weak acid?
That's an awesome question. How do you know what's a strong acid and what's a weak acid? There are 6 strong acids, and all the rest are weak. And I think we're going to get to that, but I'm not sure if that comes up in 1A. Can't remember. So strong electrolytes and weak electrolytes. Strong electrolytes dissolve completely as ions. And this includes the soluble ionic compounds and the strong acids. They conduct electricity well. Weak electrolytes, mostly molecules, they may have some ions. And so weak acids are weak electrolytes, and they conduct weakly. Not daily, not monthly, weekly. I was thinking that, but I thought I shouldn't say it. Anyway, thank you. So we saw the video, but this is what's going on here. This is useful up here, these pictures. So in a sugar water solution, there are no ions. The electrons can't flow through this circuit and light the light bulb. Acetic acid is a weak acid, and so here's one acetate ion and one hydrogen ion, but over here, most of these are intact molecules, not ions. They don't conduct electricity. We only have a few ions present. So a little bit of electricity gets through, and we get this weak glow. Sodium chloride is a soluble ionic compound. It dissolves completely to form ions, and so there's lots of ions to carry the current. We've got a lot of current, strong electrolyte. Acids ionize in solution. They were molecules, they become ions. That's what ionization means. Dissociation is the word we use when we talk about ionic compounds dissolving. An ionic compound as a solid contains ions. When we make a solution and dissolve the ionic compounds, it still has the same ions. So those haven't changed, but now they are dissociating from each other. They're like, I don't like you anymore. I'm going to go over here with my water molecules. They're distancing themselves. They're separating, so dissociating. If you have polyatomic ions, like here we have sodium sulfate, that sulfate ion is a single polyatomic ion. When sodium sulfate dissociates, the sulfate remains together. The Na2 here, that 2 is telling us there are 2 sodium ions. It's not suggesting that the formula for sodium ion is Na2. So we get 2 sodium ions and 1 sulfate ion. It doesn't come apart into oxygen and sulfur. That's why it's given a name, because it tends to stay intact. You can get it to come apart, but that's not going to happen when it just dissolves. It's not going to come apart. So, ionic compounds dissolve in water. You've got separated ions. Do all ionic compounds dissolve? No, they don't. Some do, some don't. Soluble means it dissolves in water. Insoluble means it doesn't. Now, we have to be a little bit careful there, because when we say insoluble, we mean very little of it will dissolve. Even an insoluble compound may release a couple of ions, a few ions into the solution, but they're not enough to be significant. It's not going to conduct electricity. You're not going to notice that any of it has dissolved. If we put silver nitrate into water and stir, it dissolves. It seems to disappear. If you put silver chloride into water, it's just going to sit as a lump. It's going to look like this. You're like, well, it's a little cloudy there. Those are probably small particles of the solid that will settle out eventually, but here's the silver chloride down there. It's not going to dissolve. There will be a very few ions that do dissolve, but the vast majority, probably 99.9999999% don't. Right? So how can you tell which ones dissolve and which ones don't? It's actually very complicated. Yeah. So, you know, it's complicated. There's no other way to say it. So what do you do then? Well, people have tested and to see, well, let's put some of this in water, stir it up. Did it dissolve? Yeah, it did. This one didn't. And so they tested all these different things, and then they tried to look for patterns, right, so that we could predict what's going to happen when we put something in water. This is an empirical method of predicting solubility. So they developed a set of rules. Here are the rules. These rules do not cover all of the compounds. These are the rules that I want you to learn. You need to learn these rules. So anything covered by these rules, you should be able to tell me it's soluble in water or not soluble. Okay? We might run into other things that we need to determine, is it soluble or not. We're going to look those up in a book, ask Siri or Google or somebody. I don't know, I just got distracted. Okay, so how do we use these? And they're actually not as hard to remember as it looks. So the top half of this table is talking about compounds containing the following ions are generally soluble. So these guys, if you see that in the formula, it's generally soluble except over here. In the bottom half, these are generally insoluble. Hydroxides, sulfides, carbonates, phosphates, except these guys. Okay, so this is how I would simplify this table. When we're looking at hydroxide and, let's start at the top. Okay, so lithium, sodium, potassium, those are group 1, and then ammonium. They're always soluble, no exceptions. Nitrate and acetate, always soluble, no exceptions. That shouldn't be too hard to remember. Then we've got chloride, bromide, and iodide. Those are usually soluble, except when they're with these guys. So all those words, I think, are a little confusing. So I prefer to just think of it this way, just list them over there. So these guys dissolve, except when they're with these. Sulfate compounds dissolve, except with strontium, barium, lead, silver. So I want to point out to you, here's silver and lead, there's silver and lead. The same two exceptions. So silver and lead too are often exceptions.
Is silver having a +2 charge that just charging has?
It has a +1 charge.
Oh, I'm sorry,
Lead. There's lead 2 and there's lead 4. It's lead 2 that's insoluble with these things.
The lead 4 is...
Lead 4, I would guess, is soluble. So then we get down here. So hydroxide and sulfide are generally insoluble, except. So they mention this. The way I deal with this is I always start at the top and I move down. So if my compound has lithium in it, maybe it's lithium hydroxide, and I come to this, lithium, no exceptions, I am not going to look at the rest of the table. So I don't see the need to list this as an exception down here. Hydroxide with lithium, well, that was covered up here. So in my mind, I just get rid of this part. I think it's confusing. Start at the top and work your way down until you find the rule that applies. Okay, so except here we have sulfide with these three or hydroxide with these three. Well, why label them separately? Let's just list them out there once and not worry about the rest of that stuff. Doesn't that look easier to remember?
Also listed above.
They're also listed above. These three. The same here. So those three are an exception with sulfate, and they're an exception with these two. And then for carbonate and phosphate, those are insoluble except, oh, those are those same guys up there. So there you go. Can you memorize that? You're welcome. You need to memorize that. Okay, so we talked about it, we looked at it, now we're going to try to use the picture in our head that we have of that. Wouldn't it be great if you could take a screenshot with your brain? Some people can. Predict whether each compound is soluble or insoluble. So nickel sulfide. So I'm going to mentally go through that list. As you are learning this, don't just jump to the rules and look to see if it's soluble or not. Try to picture it in your mind and go through the list and predict, and then check yourself on the actual list. So I'm going through the list and I'm like, okay, nickel wasn't on anything. Sulfide, there was the group 1s and ammonium, and then there was acetate and nitrate, and then there was the chlorides and bromides, etc. And there was sulfate, and then in the bottom half was hydroxide and sulfide. Those are generally insoluble except with those three, right? So I'm going to say this is insoluble. I'm going to go back and look at the chart. Actually, let's look at that one. Here's sulfide. Insoluble. Nickel, not one of the exceptions. Nickel sulfide is insoluble. You see how we did that? So this is in, I'm writing with white, that doesn't work, insoluble. Magnesium phosphate. So most of the things that are listed there are the anions, right? Do you remember where phosphate was? Way at the bottom. Were there any listed exceptions? Not really. We don't have lithium, sodium, potassium, or ammonium here. So we pass that up. We're going down, 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 down. We get down to phosphate. So is this soluble or insoluble? Insoluble. The only phosphates that are soluble are lithium phosphate, sodium phosphate, potassium phosphate, ammonium phosphate. But those get covered by that first rule. How about lithium carbonate? Soluble. We don't even have to go very far down the table. The first line, lithium compounds are soluble, no exceptions. Done. Soluble. Ammonium, yeah, question. Are we ignoring things that are slightly soluble? Yes, we are ignoring things that are slightly soluble. That makes just a big mess of things. So some things are slightly soluble. And it really depends on what exactly you're doing, whether you include those with soluble or with insoluble. How's that for confusing? So ammonium chloride, soluble. First row, ammonium, done, soluble. Any questions? Yes.
Oh, can you go back to the part?
Oh, no, I can't.
Oh.
Oh, man. Well, how am I going to get that then? You know what you do is you go to YouTube, you play the video on your phone, you go forward to that part, you pause it, you take a screenshot. And that'll be better than taking a picture of the screen.